Okay, ideas to implementation. Let's have a quick look at the syllabus so you get an idea. Ideas to implementation is not like the other parts of the syllabus. Because, no, there's not. Because, unlike the other parts of the syllabus, where in motors and generators we actually had sort of a sequential idea that you went from what is it makes motors and generators work through the DC motor, through generators, through transformers and so on. You can see the relationship between them. The idea that ideas to implementation have is actually held in the title of the topic. Because if you notice, an idea is a thought someone has that might lead to some sort of action. And what they do is they break up in the syllabus, I think it's 4, maybe 5 main ideas, and look at how the idea led to some changes in science and then technology, and brought about a technology we use today, kind of. So the sort of little subunits, there's not a relationship between them, they're just an idea that was had, and we trace the science through until we come to the consequence of that idea. And I think part of this topic is to try and convince people, which is well worthwhile, that science is worthwhile just doing. You can't predict where things are going to take you. So when Faraday started fiddling around with electricity and magnetism, and developed that first motor with a bit of wire spinning around the outside of a magnet in a pool of mercury, it had no practical use in the world. It had no purpose at all. It was just something that he could make happen and was interested in. But that's ended up in the consequence now where we have, all the electrical devices we have today. Because once he made the motor, his next question was, well, can I actually reverse the process and make electricity? It's his work with no practical use in the world that's led to our huge generation plants, our electrical distribution systems, our fans in our home to keep us cool, air conditioners, fridges, everything. Okay, and this topic traces through our idea. You can begin to look at stuff that looks absolutely useless in terms of practicality, but you can end up with something useful at the other end of it. And one of the problems with doing this, one of the problems you face in doing this, random comments, Riley, don't really help some ways. Okay. Let's have a very quick look at the syllabus.
She didn't just go, oh, I've got a sneeze, when's the silver thing? Like, she just sneezed when she was in front.
It's like sprinting from the front over all the way out.
All right. So, when we're doing this, we face the same problem we face with the space topic, and a lot of the stuff we're looking at is historic, and we in fact know things they didn't know when they were doing this. You might remember the HSC study day, Steve Fogel gets up and he says, all these scientists would love to know what you know now. You know more than all these famous people. Well, we're looking backwards, so we know things that the syllabus is going to cover over again. So, you look at this, and it talks about how at the beginning of the 20th century, many of the pieces of the physics puzzle seem to be falling into place. The wave model of light had successfully explained interference and diffraction, and wavelengths and extremes of the visible spectrum had been estimated. Now, notice talk about interference, diffraction, wavelengths. That's assumed knowledge out of year 11. So if you don't know what those things are, you're going to need to look back and learn what they are. The invention of a pump that would evacuate tubes to 10 to the minus 4 atmospheres allowed the investigations of cathode rays. And this is going to be one of the key concepts. X-rays would soon be confirmed as electromagnetic radiation, and patterns in the periodic table appeared to be nearly complete. The nature of cathode rays was resolved with the measure of the charge on the electrons soon to follow. There's a small number of experimental observations still unexplained, but this apparently complete understanding of the world of the atom was about to be challenged. The exploration of the atom was well and truly inward bound by this time, and as access to greater amounts of energy became available, the journey of physics moved further and further into the study of subatomic particles. careful observation, analysis, imagination and creativity throughout the early part of the 20th century developed a more complete picture of the electromagnetic radiation and matter. The journey taken into the world of the atom has not remained isolated in labs. The phenomena discovered by physicists have, with increasing speed, been channeled in technologies such as computers, to which society has ever increasing access. These technologies in turn have often assisted physicists in their search for further knowledge and understanding of natural phenomena. One of the biggest drivers in our world of the search for more efficient memory in computers and greater operating speeds is the need of scientists to actually access ever increasing computer speed for their models and things. Yeah.
Is this sort of like, communication, just like a...
No, funny enough, a lot of the stuff in the contextual outline really, in many ways, does not appear in the actual course.
The topic, because like contextual outline for us describe...
No, that's what I'm saying, and I'm about to say for you. The course itself, if you look at it, starts off looking at the development of television. And we go from electron to television. That's what we're tracing. The only problem is the television that they use in this course happens to be old cathode ray tube television, not the current technologies we use.
You know Kieran Baird in Year 9 or something? His granddad was the guy who invented the first TV, and it sounds like bullcrap, but if you look up the person who invented
possible.
the TV, it's someone Baird.
Yeah, it's his name, it's the last name there, so it's quite possible, although you'd think he'd be richer than he is if that was the case. Now, this is talking about light, and we're following the model of light to look at the idea of the photoelectric effect. Now, you might not recognise that,
Black body radiation.
And black body radiation was in space. No, it wasn't, so it was in cosmic engine. So we do need to look at that, but the photoelectric effect is actually solar cells. So we look at how we went from an idea of light to solar cells. The next part of the topic is we're looking at the invention of solid state electronics. So we look at how an understanding of properties of semiconductors led us to the point where we have transistors, and transistors are important because they are the basis of the electronic chip, which is what makes everything run. Yep.
So by the looks of this, it seems like a lot of the questions they'll ask you is going to be the multiple, they've got multiple line answer questions other than...
there's lots of calculations, and then out of this, some of the deeper ones come out of this, yeah. And this one is actually, you can see what it's about. It's about how metals at different temperatures lead to superconductivity and about its use as superconductivity. Funnily enough, they had Braggs in there, but that's only because you happen to be an Australian, so they want that in there. Superconductivity, in simple terms, is when a conductor conducts with no resistance.
No resistance.
None at all.
That happens.
We use it. MRI machines use superconductivity.
How come we don't have it as a light?
Medical resonance imaging.
We come across that, and that's the end of it there. So if we go on to do medical, then you'll learn about MRI and about that stuff. Okay.
I want to be a doctor too, but that
No, I refuse. I refuse to do astrophysics.
Why?
The first thing that we need to understand in this course is the relationship that there is between science and technology. Science discovers things which drive technology, and then how technology in turn changes what scientists can do and then changes their discoveries. Yep.
Yeah, I read about like a thing that like there was this game or something on the web where you can build some sort of enzyme, and they put like an enzyme or something that they could build on there that scientists couldn't figure out, and give them a couple of weeks to figure it out.
Yep, and then they'll find a use for it, and then that will raise other questions back and forth. Exactly right. Okay. So, yep, you can ask that. Well, if we have a good understanding of, you have a good understanding of the genome, it gives you an understanding, about which genes to look at, or what genes are there and what you can look at, and see which ones switch which body processes. And then if you know which body processes switch on and off by which genes, then you can do diagnoses with it, or you might even be able to make treatments for things, which are really important. But yes, there are. But that's one of the reasons we needed incredibly powerful computing, because of that sort of thing. So we've mapped it broadly, but there's still a lot of detail in there missing. They've just added a couple of new letters into the DNA sequencing from some discovery. I'm not sure. Now, I have to put this very, very carefully. I only read the article very in skim reading, and I noticed these had added 2 new letters in for some sequencing for some reason. I haven't looked at what genome, and I haven't looked at why. So I can't tell you that that's important for human genome or anything, but it's there. Okay.
What about ASTC? Old style.
Okay. From early times, people have been fascinated by electricity and how it works. And there's a great special I could show you. In fact, I think I showed you 10 a while ago, called The Story of Electricity. And there's some I've got it on here, but I'm not going to show you today. And there's some beautiful scenes where you had people trying to work out how to store charge. I think I showed you the Leyden jar bit of it. Leyden jar. Because I'm sure we made a Leyden jar as just a bit of a dem in our Year 11 course. No? Okay. A Leyden jar is just a way of storing electrical charge. You build it up. It's first capacitor. No, what you do, the easy way to make it, and you can do it at home if you like. What you do is you get a plastic cup. You get a foil pie dish, right? And you get a piece of wire, and you get some water. That's a Leyden jar. And then you connect this up to some sort of power source. Doesn't matter which way around particularly. And because it's got an insulator on the inside, right? You get and that's a conductor. You get a collected charge on the metal plate, and you get a collected charge on the interior of the cup. And then if you take a earth wire and connect it up, you get a spark.
No, we did something else, but it was similar. It was like a plastic cup.
Wires. It was not like a simple one in one end and one in the other, then put it through.
But it wasn't this.
No, that was a coil. That was a coil where you're doing something different. Okay. So people were experimenting with this stuff called electricity. There's a beautiful picture in it too, where they got a young boy on a wooden swing with some silk ropes, and they charged him up with a particular. They used to charge him up spinning a glass bottle and put his hand on it, and they put gold leaf on the floor, and they swung him across it with his hand out, and the gold leaf would jump off the floor, hit his hand, and bounce down again. It looked really, really pretty good. But there were serious issues technologically with experimenting with electricity. One, you need a source of electricity, and two, you needed an environment where electricity was free from interference in its passage, right? And you had to be able to see it. And that necessitated the inventing of something called a vacuum tube. Right. Now, if you create a vacuum tube, that's a tube where you can suck all the gases out of it, or a large amount of gases out, and get a very low pressure inside of it. And then you can if you can get a large enough charge, you can pass a current across it, and it will do things in there. Well, the glass tube is insulated, but what's happening is instead of having the gas interfering with the passage of the electricity, it can just flow fairly freely through. Now, I'll show you a brief video of something we're going to look at tomorrow, but in the meantime...
We all do it like you, right?
Yep, that's right.
Are those two pipes that run?
No, we're going to do something a bit different than that. What we're going to do is we're going to emulate this particular thing I'm going to show you now.
that for the cathode?
Yes, it's cathode rays, that's right.
What's a cathode ray oscilloscope? We use that earlier.
That's like the TV. Okay, this is what we're going to be looking at, I hope. Let's see what happens here. Right. So, I'll stop this. What you got there, you got, particularly, you got some gas in there. What he's doing is he's pumping the oxygen out using a vacuum pump, and watch what happens as he does. Changes current, changes characteristic. So as they learned about vacuum jars, they're able to see things happening with this electricity. It's quite slow what he's doing. For us, if we get to this point, the quick thing that the syllabus wants you to know is just what was the development of this of the technology that was needed to be able to do this stuff with, and then we need to look at what it does and explain it. Okay, so today's job is quite easy. On page 186, 187, and 188, I think it is, of the text. It's just an outline of the technology change from the very early Botticelli tube through to the Geissler vacuum pump and Geissler tubes. That comes later. That's Crookes tubes and things. Yeah, all that's later. So what we're going to do today is I just simply want you from page 186 to look at the part on the development of the vacuum tube, and just make a little timeline up of the key dates involved in the development of that thing and the names. There's about 4 or 5 names you need to know. And I'll also give you ideas to implementation, because that has more people named in it. People like Luca and a few other people in there. Okay, so that's just a simple task. You can put a new heading, ideas to implementation. You can just write down the 4 or 5 most significant dates and what they're about in just very simple summary form. Now, there's something that I should tell you about this, is that you notice that, notice with the names up here, and there's a large number of British scientists who are pretty preeminent at the time. There's also a large number of European, largely German scientists. And as they experimented and looked at what cathode rays were and tried to work out what they are, they ended up with basically 2 schools of thought. One lot the British supported, one lot the Germans supported, and then up in a decades-long argument between the British and the Germans about what cathode rays were made of. Einstein in the end.
Germans.
Did Germany win the World Cup?
No, they lost.
Did Germany beat Brazil?
Yep.
What was that?
You're talking about the soccer, we're talking about World War II.
Damn, that just happened.
One of them made from 7 to 1. 7 to 1.
So Germany never won something.
Wasn't Russell that first to join the German World Cup?
That's why they wear orange.
That's what we won.
Then you still know that they're there.
That's why Germany wear white. I think they always wear white and Germany wear the
Owen must wear orange because otherwise no one would realise them on the second place podium.
Now here's a famous name you will come to know more. Heinrich Hertz. And he did an experiment where he made observations which were later shown to be not true.
Oh no.
I love that people are famous for saying the wrong thing.
No, he's famous for doing some right stuff too.
Okay, like some people are famous for doing the wrong thing.
Like the person that said
That's a quick thing.
Right, did you actually go on a flat
I did.
Really? And?
It's your short hair right
Oh my god.
And I wish we'd been to space and seen them ground. No, it's flat.
Have you been to space? No, so you don't know.
It's flat, and you can either see the bending of light and
That's one job. I'm having a pretty good time yeah, I'd rather stay in the go out there. I'd rather stay in here. If you got a telephone, it's here. They're going to get the ring telephone. Yeah. Call telephone with a real one, and that's not big. But how did you supposed to get?
They never got captured.
Wasn't there one guy about this whole thing that he oh no, it was like special or something, and he released the first picture?
No, there was
The original myth.
yeah.
Well, there's an original first one. Yeah, the first. And then Neo came on with I got more to there's one dude, who's the original dude here? Thomas. He's just Thomas. Thomas, I think, because they had the one person. No, there was one. There were. No, what's the one? There was people on the outside, and they found the person and they found someone like me.
right.
Or there was supposed to be someone like me.
Explain it all.
But what I don't want to put down to be able to do is shit. What I get is that
From what I
like some people,
there was one
what's not?
person falling within it.
That's the city of the rebel.
That's the last city. You know, in the war.
Yes.
Because he goes, he challenges the human food. Yeah, but the one that made it out.
The one that voice later.
It's a voice in thing.
Oh, okay.
Yeah, I know Hugo. He played Kyle for something. I can do that in the real world.
I said if anybody else.
So, Riley,
It's actually 12 and a half.
Riley, how about you get on, do what you need to do here? Cody, how about you? What are you going to do? Are you going to get this off the computer tonight, or what are you going to do with these notes?
There's like they punching so quick it slows it all down.
What's on the song, bro?
Well, that's basically in the timeline anyway.
There's a fish small without it, but want to come back in.
That'll be on there.
That's cool.
Putting on there now. It's done actually, it's on there.
They're up in the air and they go to